right, section 5.7. When we get done, we'll be able to define what an arithmetic sequence is and what characterizes an arithmetic sequence, find a particular term of an arithmetic sequence, find the sum of the first n terms of an arithmetic sequence, and also we'll be able to define what a geometric sequence is and how it differs from an arithmetic sequence. Be able to find any term of a geometric sequence and find the sum of the first n terms of a geometric sequence. All right. Basically, what is a sequence? A sequence is a function where the domain is the set of positive integers or the set of counting numbers. Each number of a sequence is designated as being a term of the sequence. Suppose a young couple determines that they can afford to sock away $400 each month to save for a down payment on a home. They don't trust banks, so they plan to put $400 in cash in their cookie jar each month. The amount they would save would grow like this as the months progress. So the first month they would save $400. After 2 months, they would save another $400, which means their balance in the jar would be $800. After 3 months, their balance would grow to $1,200, then $1,600, and then $2,000, et cetera, et cetera. All right, this is called a sequence in mathematics. The first term of the sequence is 400, the second term is 800, the third term of the sequence is 1,200, the fourth term is 1,600, and the fifth term is 2,000. This is a special type of sequence called an arithmetic sequence. Right? So what is an arithmetic sequence? A sequence is arithmetic when it possesses what is called a common difference. That's to say, when every term after the first term is obtained by adding the same fixed difference or number to the previous term. For instance, here's an arithmetic sequence, 1, 3, 5, 7, 9, 11, ... This is called an infinite arithmetic sequence in the sense that it goes on forever. The common difference would be 2. And the difference is 2 because to move from one term to the next term in the sequence, you have to add 2. So this is called an arithmetic sequence where the common difference is +2. Okay. All right. Here's another example of an arithmetic sequence, 2, 7, 12, 17, 22, 27. The common difference of this arithmetic sequence is 5 because you have to add 5 to any term of the sequence to advance to the next term. It's called an arithmetic sequence. So all arithmetic sequences have a common difference. The common difference of this arithmetic sequence is -3, where you have to keep adding -3 to a term to keep advancing to the next term. The common difference of this arithmetic sequence is going to be 1/2. You have to keep adding 1/2 to move to the next term. So all of these sequences are called arithmetic sequences. Any questions so far? All right. Here are some examples. The value of an account that starts with $700 and has $80 deposited each month would be an arithmetic sequence in the sense that the first term would be $700, the next term would be $780, the next term would be 780 plus 80 more, which is $860. 860 plus 80 more gives us the fourth term, which is $940. Plus $80 more is $1,020. This is an example of an arithmetic sequence. All right, here's another example of such a sequence. First term is 9, and the common difference is 7. So listing the first 5 terms of this arithmetic sequence, we would have 9. 9 plus 7 is 16. 16 plus 7 is 23. 23 plus 7 is 30. 30 plus 7 is 37. That's an arithmetic sequence. Okay. Here's another example of an arithmetic sequence. The first term is 1/16, and the common difference is -1/8, which we start off with the with 1/16, and then we move to the next term by subtracting off the common difference, which is subtracting off -1/8, subtracting off 1/8 rather, or adding -1/8. And 1/16 minus 1/8 is the same thing as 1/16 minus 2/16. And you can see that you would get -1/16 as being your next term. -1/16 minus 1/8 more, or minus 2/16 more, is -3/16. Minus 1/8 more, or minus 2/16 more, is -5/16. And then subtracting off 1/8 or subtracting off 2/16 more, you get -7/16. So that's an arithmetic sequence. Any questions about these? Arithmetic sequences. All right, normally, symbolically, we like to use lowercase letters to represent terms of a sequence, and A is usually a favorite with most textbooks. The symbol A_1 represents the first term, A_2 represents the second term, A_3 the third term, and so on. So an arbitrary sequence looks like A_1, A_2, A_3, A_4, A_5, ... We call A_n the nth term of the sequence. So notice the first term is A_1. The second term can be obtained by adding to the first term the common difference. True? Okay, in fact, I want to show you something here. Suppose we start with an arithmetic sequence where the first term is A_1. The second term is the first term plus the common difference. The third term is the previous term plus a common difference. The fourth term is going to be the previous term plus a common difference, etc., etc. All right, so the first term is the first term, A_1. The second term we see is the first term plus one common difference. The third term is A_1 plus two common differences, which is to say your first term plus 2 times your common difference. The fourth term right here is your first term plus 3 common differences. And in general, it won't be our nth term. Our nth term. Well, I want you to pay attention to the term index. This is called the index, and the coefficient in front of D here. When the index is 2, denoting our second term, we have 1 in front of D. When our index is 3, denoting our third term of the sequence, the coefficient in front of D is 2. When our index is 4, the coefficient in front of D is 3. When our index is 1, technically the coefficient in front of D is 0. All right. Can anybody help us generalize then what the nth term of such a sequence would look like? Notice with all these terms, the first term is always present. The first term is always present. So I'll bet dollars to donuts on our nth term, we're going to have our first term present too. Plus what? How does the coefficient in front of D relate to the index of the term number? How does it relate?
It's going to be 1 less than the term number.
1 less. So therefore, our nth term is going to be the first term plus n minus 1 times D. And we have arrived at something very important here. This is called an nth term rule for an arithmetic sequence. The beauty of this rule is it can help us generate or crank out any nth term of an arithmetic sequence, as long as we know the first term and we know the common difference. So this is a very important formula to memorize, for an arithmetic sequence. It's called the nth term rule for an arithmetic sequence. Okay. I would recommend you just memorize that or have it handy. So here they're showing how we derive the The ultimate derivation is the nth term rule of an arithmetic sequence. All right, let's see if we can use it. Find the value of the account in example 1 after 14 months. And recall that example 1 was we started with $700 and we add $80 each month. So the first term would be $700. The common difference is $80. And they want us to find how much money is going to be in our account 14 months after the first month. They want us to find the 14th term of this arithmetic sequence here. To find the 14th term, we use our nth term rule that we just developed. To find the 14th term, we need our first term, which is $700 plus 14 minus 1 times the common difference of $80. So it's going to be $700 plus 13 times $80 over $700 plus $1,040, which gives us $1,740 as being the amount of money in our account 14 months from the first month. All right. So that's the nice thing about an nth term rule is you can use it to crank out any term of the arithmetic sequence, any term you desire. Any questions about that? What just happened there? All right, now in this example, they want us to find a particular term of an arithmetic sequence. They want us to find the 10th term of an arithmetic sequence, with the first term being 1/7 and the common difference being 2/5. So what do we know? We know the first term, a sub 1 is 1/7. We know that we want to find the 10th term, so n is going to be 10. And we know the common difference is positive 2/5. So to find the 10th term, we again turn our attention to the nth term rule. And in this nth term rule, n is going to become 10 because we want to find the 10th term denoted as a sub 10. First term is 1/7, that replaces a1. The common difference is 2/5, that replaces d. N is replaced with 10. We go through the arithmetic. So our 10th term is going to be 1/7 plus 9 times 2/5, which when you get done with the arithmetic, your 10th term will be 131 over 35 for this arithmetic sequence. That's your 10th term. Any questions how we found the 10th term? All right. Now, suppose we're given an arithmetic sequence and they want us to find the sum of the first n terms of the arithmetic sequence. Well, the sum of the first n terms of an arithmetic sequence is given to us by this formula here. And I can show you how this formula comes into existence. I can show you the derivation of that formula. It hangs out in my college algebra book. Let's go grab it. Wait a minute here. Okay. All right, so I want to show you where this sum of the first n terms in arithmetic sequence formula comes from. And I'm going to show you how to derive it, ladies and gentlemen. Okay. Suppose No, let's just go down here. All right, so the sum of the first n terms in arithmetic sequence is going to be the first term added to the second term, added to the third term, added to the fourth term, added to dot, 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 added to all the way to the nth term. Well, the first term is a sub 1. The second term is a sub 1 plus the common difference. The first term plus common difference. The third term is the first term plus 2 times the common difference. The fourth term would be a sub 1 plus 3 times the common difference, plus dot, 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 plus all the way up to the nth term. What if we compute the sum of the first n terms now by basically rearranging these terms of the previous sum by having the last term go first and the first term go last? So we're going to flip all these terms around. So the sum of the first n terms could also be expressed as the nth term added to the term that's previous to the nth term, which is to say the nth term minus a common difference, plus the term, 2 terms previous to the nth term, which is the nth term minus 2 times the common difference, plus dot, 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 plus all the way back to adding the first term. Notice something interesting happens here. If I add these two together here, these two identical sums, s sub n plus s sub n is 2s sub n. And notice when you add these together, you're left with this. What happens when you add these two together? What drops out of the picture?
The D's?
The D's drop out, and we're left with a sub 1 plus a sub n. In fact, what happens when I add any subsequent terms of these sums? The D always what? Drops out, doesn't it?
Yeah.
You know that? Ladies and gentlemen, look at what interesting thing has occurred here. We discovered that 2 times the sum of our first n terms in arithmetic sequence is really equal to the sum of n of these terms, a sub 1, and the first term added to the nth term. So we can rewrite the right side as n times a sub 1 plus a sub n. Solving for s sub n, dividing both sides by 2, we develop our formula here. Everybody see that there? There's your formula. See how that comes into existence? Now, you're not responsible for that derivation. I just thought I'd show you it so you can appreciate where the formula comes from. It didn't just get dropped off by a UFO. It actually has a derivation. All right. All formulas in mathematics have a derivational proof, ladies and gentlemen, because the entire field of math is a logical field. And all theorems and corollaries and things we use in math to work with various constructs have been proven and do have proofs. You'll start writing proofs if you get into your junior year at a university if you major in mathematics. Okay, you start writing proofs of theorems. All right, so how did we get on this topic here? Well, back to the PowerPoint. So there's the formula. You now know where it comes from. And the nice thing about this formula is it can literally enable us to rather effortlessly compute the sum of the first n terms of an arithmetic sequence. As long as we know how many terms we want to add together, that'll be n. We know the first term, and we know the last term of our sequence that we need to add. And we'll divide that by 2. Okay. All right, so here's an example. Suppose that we put aside $10 this month, then $15 next month, $20 the following month, and so on. This time, it's the amount you're saving that forms an arithmetic sequence because it's going up by $5 each month. So rather than the value of the account, in this case, it would be of interest to find how much you put aside in, let's say, the 14th month. But it would be a whole lot more useful to find the sum of the contributions for the first 14 months. So to find the sum of the first 14 terms of the sequence of the deposits described in the text above, So how would we do this? Well, first we need to find the 14th term. That is the, we need to use the nth term rule to find the 14th term. Or the 14th number that, or amount that's added to our sum. And we use our nth term rule that we developed. And we know our first term is 10. We know we want to find our 14th term, so n is 14, and our common difference is 5. So the common difference is 5 because the amount of money that we save each month increases by $5 each month. Notice that. All right, so what would be our 14th term? Well, plugging in our first term, 14 for n, and our common difference is 5. Our 14th term would be $75. Now, I have a question for you. That $75, does that represent the amount of money we have in our account after 14 months? Or does
No,
that represent the amount we're going to sock away during the 14th month? What do you think?
I think that's the amount we're gonna sock away with the 14 months.
That's right. That's the amount of money we're going to put into our account the 14th month, the $75. That doesn't mean we have $75 in our account. Okay, that just indicates the amount of money we're gonna, put into our account or save for the 14th month. Now, ladies and gentlemen, to find the sum of all these deposits over a 14th month period, we want to find the sum of the first 14 terms then of this arithmetic sequence, which is 10, 15, 20, 25, 30, 35, 40, 45, all the way up to $75 being deposited the 14th month. So we need to know n, and since we're trying to find the sum of the first 14 terms, n is 14, the first term is 10, and the last term, the 14th term, is $75. Plugging things in, going through the arithmetic, we discover that the amount of money we'll have in our account at the end of the 14th month would be $595. That would be 10 plus $15 plus 20 plus 25 plus 30 plus 35 plus 40 plus 45 plus 50 plus 55 plus 60 plus 65 plus 70 plus $75, correct? That would be $595. Pretty neat, huh? Saves a lot of time. All right. So we have discussed an arithmetic sequence. Now we'll turn our attention to another important sequence called the geometric sequence. What characterizes a geometric sequence? Well, a geometric sequence and all geometric sequences have what is called not a common difference, but a common ratio. All geometric sequences possess a common ratio. It's a number that indicates what we would have to multiply a term of the geometric sequence by to advance to the next term. In other words, if you look at this sequence here, this is not an arithmetic sequence because 3 minus 1 is 2, but 9 minus 3 is 6. So there's no common difference here. We don't add a common number to any term to advance to the next term. So this is not arithmetic, but is it geometric? The answer is yes, because if I take 3 and divide it by the previous term of 1, that ratio is going to be equal to the ratio if I take 9 and divide it by the previous term of 3, which is going to be equal to the ratio if I take 27 and divide it by the previous number, which is 9, which is equal to the ratio of 81 divided by the previous term in this sequence, which is 27. All these ratios appear to be giving us what? 3. So we would say this is a geometric sequence with a common ratio of 3. That's also to say that to move from one term of the sequence to the next term, I would not add 3, I would multiply by 3. So to go from 3 to 9, I would have to multiply by 3. To go from 9 to 27, I would have to multiply by 3, etc., etc. Here's another geometric sequence whose common ratio is going to be 5. To find it, it's a simple matter of dividing 10 by 2, or dividing 50 by 10, or 250 by 50, or 1250 divided by 250. You'll get a common ratio of 5. This geometric sequence is called an alternating geometric sequence because the terms alternate in sign. Positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative. It's called an alternating geometric sequence. And the common ratio can be found by taking -10 and dividing it by 5, or 20 divided by -10, or -40 divided by 20, or 80 divided by -40, which in each case you're going to get -2 for the common ratio. So that's what you would have to multiply any term of this geometric sequence by to advance to the next term, is you have to multiply it by -2. This next geometric sequence has fractional entries. And to find the common ratio, we would take 1/4 and divide it by 1, or 1/16 divided by 1/4, or 1/64 divided by 1/16, or 1/256 divided by 1/64. In each case, you would keep cranking out this common ratio of 1/4. Or you could think of it this way: to move from any term to the next term in this geometric sequence, you'd have to multiply by 1/4. All right. Any questions about a geometric sequence? So an arithmetic sequence has a common difference. A geometric sequence has a common ratio. Night and day difference. All right, here they want us to write the first 5 terms of a geometric sequence whose first term is 4 and the common ratio is -3. So we start with the first term, which is 4. That's a sub 1, that's your first term. Your second term is going to be found by taking your first term and multiplying it by the common ratio, which is to say, we multiply the first term by -3. So 4 times -3 gives us -12. If you multiply -12 by -3, you get +36, etc., etc. So this is an example of an alternating geometric sequence. Any questions with what happened there? How we wrote the first 5 terms there of that geometric sequence. All right, now how would we develop an nth term rule for a geometric sequence? Well, we do so similarly as how we developed it for an arithmetic sequence. The first term of a geometric sequence is a sub 1. The second term is found by taking the first term and multiplying it by the common ratio. Third term is found by taking the previous term and multiplying it by the common ratio. The fourth term is found by taking the previous term and multiplying it by the common ratio. Next term is found by taking the previous term and multiplying it by the common ratio. So the first term is the first term. Second term is going to be the first term times the common ratio. The third term is going to be the first term times the common ratio squared. The fourth term is going to be the first term times the common ratio cubed. The fifth term is going to be the first term where the common ratio is the first term times the common ratio of r to the 4th power. So in general, what's going to be my nth term here? Can we see how this generalizes here? Technically, this is a sub 1 times r to the 0th power. R to the 0th power is 1. I want you to pay attention to the index of the term and the power on r. 1, 0, 2, 1, 3, 2, 4, 3, 5, 4. And what? And what? What's going to be the power on r for my nth term? How does the power on r relate to the index of the term number?
1 less.
1 less. So the nth term is going to be my first term times r raised to the 1 less power than n minus 1th power. Ladies and gentlemen, you have your nth term rule for a geometric sequence. This rule will crank out any term of a geometric sequence, so long as you know the first term and you know its common ratio. You can crank out any subsequent term. This is an important formula. I would recommend you memorize that. This is the nth term rule for a geometric sequence. All right. See that there? Okay. So that's where that formula comes from. All right. All right, let's employ it. Here's an example. Suppose we want to find the 12th term of a geometric sequence where the first term is 1/2 and the common ratio is 6. So we know a sub 1 is 1/2 and the common ratio r is 6. They want us to find the 12th term. We're going to use our nth term rule to do so. So we want to find the 12th term. So n becomes 12 in this formula. A sub 1 is our first term, which they tell us is 1/2, and the common ratio r is replaced with 6. So we have 1/2 times 6 raised to the 11th power. We're going to need to use a calculator to help us out here. What's 6 to the 11th power? That's going to be a big number. It's 6 times itself 11 times. Divide that by 2, and you generate your 12th term as being 181,398,528. That would be the 12th term of this geometric sequence. All right. So again, the first term would be 2. If I multiply 2 times 6, 6 times 1/2 would be 6 halves, which is 3. 6 times 3 is 18. 6 times 18 is 102. Etc., etc., etc. All the way up to our 12th term, which would be this big old term right here. So that'd be the 12th term of that geometric sequence. That's a huge term. But you got to understand, we keep multiplying every term by 6 to advance the next term. It's going to grow kind of quick. Questions on that? Now, how would we add the first n terms of a geometric sequence together? Well, there is a derivation for this formula. And I'll show you where it comes from. All right, suppose we want to find the sum of the first n terms of a geometric sequence denoted as S sub n, the sum of the first n terms. Well, it's going to be the first term added to the second term, added to the third term, added to the fourth term, added to the fifth term, added to the sixth term, added to ... added all the way to the n minus 1th term, and then finally the nth term. All right. Now, suppose we put this sum in the order that we see it right here. We put it here. But let's suppose that we then take this sum formula and multiply both sides by r. So I'll multiply the left side by r and every term on the right side by r. A sub 1 times r, A sub 1r times another r is a sub 1r squared. A sub 1r squared times another r is a sub 1r cubed. A sub 1 times r to the n minus 1 power, when you multiply by r, what do we get? Well, when you multiply like bases, we had exponents. So this is going to be r to the n minus 1 plus 1 power, which is going to be r to the what? Nth power. Okay, last term. Now check this out. Suppose I take this first sum and subtract off the second sum. So on the left side of this equation, I get s sub n minus r times s sub n, a sub 1 minus a sub 1 r, plus a sub 1 r minus a sub 1 r squared, plus a sub 1 r squared minus a sub 1 r cubed, etc., etc. I continue to do that with all the other terms on down the line. And at the end, I have a sub 1 r to the n minus 1 power minus a sub 1 r to the nth. Well, something interesting happens here, ladies and gentlemen. What do these terms add up to? What happens to these terms here? So what happens to those terms?
They drop
They-
down.
They drop out. They cancel out to 0. And check it out. Isn't that going to happen with all the other ones then? You add these together, they drop out to 0. When you add these to the next ones, they're not showing the next ones, but trust you me, they would drop out. And the previous one to this one, which would be negative a1 times r to the n minus 1 power. When you add it to this guy, these would drop out also. So when we drop all those terms out, we're going to be left with s sub n times r minus r times s sub n is equal to a sub 1 survives, and this term survives at the very end. Now they factored s sub n out of both these terms here, this term and this term, because it's a common factor. Then they divided both sides by 1 minus r. And when you divide both sides by 1 minus r, you're left with this formula. That's where the formula comes from. So the sum of the first n terms of a geometric sequence is really equal to the product of the first term right here and 1 minus r to the nth power divided by 1 minus r. And hence you have your formula. Notice r cannot be equal to 1. Why do you think it's important to add this important little disclaimer here? Why can r not be equal to 1 for that formula?
Because
If r is 1, what happens to the denominator of that formula? 1 minus 1 minus 1.
Just be 0.
And you can never divide by 0, can you? Division by 0 is undefined. For that reason, the common ratio of a geometric sequence cannot be 1, ladies and gentlemen, if we are to use this formula, simply put. Okay. All right, so that's where the formula comes from. You're not responsible for that derivation. I just thought I'd show you where it comes from. Okay. And there it is. But this is a formula worthwhile memorizing. This gives you the sum of the first n terms of a geometric sequence there. Okay. And let's use it. Suppose you want to find the sum of the first 15 terms of a geometric sequence where the first term is 8 and the common ratio is -1/2. Well, we know the first term is 8. We know the common ratio r is -1/2. We want to find the sum of the first 15 terms of this geometric sequence. And so we use our formula. So the sum of the first 15 terms has us replacing n with 15 in the formula. A sub 1 is replaced with 8. R is replaced with -1/2. going through the arithmetic and actually using a scientific calculator to raise negative 1/2 to the 15th power, you're going to need to have a calculator for that. Let's see if we can do this. I'll show you on the calculator how I would do it here. Hold on a second here. All right, so I'm going to type in my numerator is going to be 8 times open parenthesis 1 minus negative 0.5 raised to the 15th power. Close parenthesis. And that's all going to be divided by open parenthesis 1 subtract negative 1/2, which I will cite as a decimal 0.5. See how I typed it all in using my parentheses here? Hit enter and boom, we get a sum of 5.333. Okay, that would be the sum of the first 15 terms of that geometric sequence. Any questions how we did that? So the first term again would be 8. The second term would be found by taking the first term multiplied by negative 1/2, which would be negative 4. Third term is found by taking the second term and multiplied by negative 1/2, which would give you 2. The fourth term is found by taking the previous term multiplied by negative 1/2, which would be a negative 1. The next term is found by taking negative 1 multiplied by negative 1/2. In this case, you get 1/2. 1/2 times negative 1/2 is negative 1/4, etc., 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 etc. This is called an alternating geometric sequence because the signs alternate from positive to negative to positive to negative. If you add together the first 15 terms of this geometric sequence, you would get 5.33. Okay. You see how these formulas are working here and how they're helping us out here. All right, let's get back to our money problem here. We began this section with an example in which a couple is saving money for a down payment on a house. Suppose that your plan is similar, but you decide to put away $150 the first month, $175 the second month, $200 third month, and so on. Would you save more or less in the first 2 years than if you put away $400 each month? Would you save more or less in the first 2 years? Would you save more or less in the first 2 years than if you put away $400 each month? So in other words, they want you to try to compare an arithmetic progression with a geometric progression. Which one would help you save faster? Well, if we list, what's that?
Oh, no, my bad.
Which one do you think it might be, arithmetic or geometric?
Arithmetic.
We'll find out. That's an interesting thing here. Let's see which one would save us more money quicker. Well, suppose that we list the amount saved each month. If we do that, we get an arithmetic sequence. 150 saved first month, 175 the second month, okay, 200 the third month, etc., etc. That would be an arithmetic sequence then, because the common difference would be $25. Find the amount that we would have after 2 years. We would use the sum of the first 24 terms of our arithmetic sequence formula. But in order to do that, we need to know the 24th term of our sequence. In order to find the 24th term of this arithmetic sequence, we would turn our attention to the nth term rule formula we developed. So the 24th term, in other words, the amount of money we'll save during the 24th month, is equal to the amount of money we saved the first month, which is $150, plus 24 minus 1 times the common difference, which is $25. So we would save $725 the 14th month. I'm sorry, the 24th month. The 24th month, we would sock away $725. Well, let's find out how much our account would grow over the course of 2 years. So how much money will we have in our account after 2 years, after 24 months? And is 24 in the formula? Our first term is $150. The 24th term was found to be $725. Going through the arithmetic, we would have $10,500 in our account at the end of 2 years. Let's contrast that with this new situation. Suppose that we put away $400 each month. What would be the total after 2 years? Well, I'm putting away $400 each month. And for 24 months, we would have simply 24 times $400, which would give us $9,600 in our account. So it looks like the first plan actually affords us more money in our account at the end of 2 years, as opposed to if we just socked away $400 each month. So having the amount you sock away increase by $25 a month for 2 years affords us a larger balance of $10,500 compared to $9,600. So we kind of got our answer here. All right. All right, here's another beauty of an example. When a worker earns a 4% raise each year, to find his or her salary in any given year, you would multiply the salary from the year before by 1.04. Why is that? Well, let me show you. Suppose you make, let's say, $25,000 in a year. Let's say. Suppose you get a 4% raise each year. So what are you going to be making next year? Well, next year, ladies and gentlemen, you're going to be making your $25,000 you made the previous year. That's a given. Plus, you're going to earn 4% more above and beyond that. That's to say 0.04 times 25,000. And what would that give us? Well, 25,000 plus 4% of 25,000 means next year we'll be making $26,000. Well, check this out. Do you agree that between both these terms there is a common factor of 25,000? So we can factor the 25,000 out of both these terms here. So I can factor $25,000 out of both terms. And when I do so, I'll leave behind 1 plus 0.04. Now what's 1 plus 0.04?
$1.004.
1.204. So you know what, to multiply a number by 1.04 means that number is going to grow by 4%. That's what I wanted to illustrate. So when you multiply your starting annual salary of $40,000 by 1.04, that will indicate the amount of money you'll make the following year. And then when you multiply the following year's salary by 1.04 again, that indicates how much you're going to be making the year after that. Times 1.04 again indicates another 4% raise, the amount of money you'll be making a year after that year, et cetera, et cetera, et cetera. Okay. So since the salary gets multiplied by 1.04 each year, we're talking about a geometric sequence here, where the first term is 40,000. All right. First term is 40,000. The common ratio is 1.04, so the second term is found by taking 40,000 multiplied by 1.04. And to get the third term, you'd multiply this by 1.04. Et cetera, et cetera. So you got 40,000 times the common ratio, which is 1.04, raised to the n minus 1 power. So that's a geometric sequence because the common ratio is 1.04. Okay. All right, so to determine how much money or what salary we will be making after 10 years at this company, we use our sum of the first n terms of a geometric sequence formula. Our first term A1 is 40,000. Common ratio is 1.04. That indicates a 4% raise per year. We put 1.04 in for R, and N is 10. Going through the arithmetic, we crank out our salary after 10 years, which should be up to $480,244.28. That's a 4% increase per year for 10 years. Let's show you how we can do that on our calculator. All right, so I'm going to try open parenthesis 40,000 times 1 minus and it's raised to the close parenthesis, divided by open parenthesis 1 minus 1.04. Close parenthesis. That's how you type it in on the calculator. You need to use those parentheses, otherwise you're going to get a logical error. You don't use the parentheses that I typed in here. You got to have all those parentheses in place. Parentheses force precedence according to the order of operations in mathematics. You got to have all these parentheses in place. See that there? Hit enter, and that would be your salary 10 years from now. Any questions? All right. Okay, that's the end of this. Let's see if we can go have some fun now. Let's see. All right, so we're gonna look at 5.7. And as always, ladies and gentlemen, it's probably wise to, look at some of these examples in your textbook. I think your author, let's see, your author derives some of these formulas. No, they're not derived the way I showed you in my other textbook. All right, let's go down and see what kind of problems we can run into. All right, problem number one. If we're given a list of numbers, how can we, could anybody explain for us how we can determine if it's an arithmetic sequence? How would we know if it's an arithmetic sequence?
Um,
Arithmetic sequence must have a common what? All arithmetic sequences must possess a common
number.
common difference, right? Common difference. How would we know if we have a geometric sequence? Number two. All geometric sequences must possess a common
Multiplier.
a multiplier or common ratio, exactly. All right. What does a sub n represent in any sequence? What does that notation represent, a sub n?
One of the terms.
Yeah, it represents the nth term of that sequence. What does s sub n represent for any sequence?
The sum of the nth term.
Yeah, for the sum of the first n terms of the sequence. Okay, good. Anybody give me an example, maybe a quantity in our world that, you know, represents an arithmetic sequence of any kind? Any sort of quantity or anything in our real world that could be modeled according to an arithmetic sequence or an arithmetic progression, as they're sometimes called. Anybody?
Are you asking how will we use this in our world?
Well, I'm saying, is there an example in the real world? You know, I'm thinking like an auditorium. An auditorium could have, you know, the further you go back, the auditorium opens up. So the closer you are to the stage, it might have maybe like 4 seats. And then maybe the second row, maybe it has like maybe 8 seats. And then the third row would have what? Maybe 12 seats. And then 16 seats as it widens out. So basically, maybe an outdoor amphitheater or something like this would kind of like go like this. Do you agree? Where this is the stage right here, right? And you have fewer seats here, and the further you go back, the number of seats in each row what increases. That would be an example of an arithmetic sequence. Do you agree? 4, 8, 16. What would be the next term of the arithmetic sequence? 4, 8, 16. What's the 20? Yeah, common difference is 4, right? And then 24 and 28. Common difference would be 4. Okay. That's an example of a sequence, maybe. The number of seats in an amphitheater or a theater. All right. What does it mean for a sequence to be called an alternating sequence? What does that mean? Alternating?
That
Every other term is either a positive or a negative number.
And the signs of the terms alternate, correct? Between positive and negative. Positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive, negative, positive. It's called an alternating sequence. All right. Let's see what else we got here. All right, ladies and gentlemen, for problem number 9, this will be classwork number 1. They give you the first term of an arithmetic sequence. This will be classwork 1. First term they give you the common difference. I want you to answer A through D for number 9. I want you to find or write down the first 5 terms of the arithmetic sequence. What's the common difference? What would be the 12th term? And what would be the sum of the first 12 terms? Go ahead, do number 9 there. Classwork number 1. 9, A through D. All right, let's take a look here. First five terms of this arithmetic sequence would be 1, 7 through 13, 19, 25. Common difference is 6. The 12th term is found by using your nth term rule, where n is 12, first term is 1, and the common difference is 6. It's going to be 1 plus 12 minus 1 times 6, 1 plus 11 times 6, 1 plus 66. 67 will be your 12th term. Then to find the sum of the first 12 terms, it's going to be, this will be 12 times your first term plus your 12th term divided by 2. So 12 times 1 plus 67 divided by 2 is 408. Did anybody get those? Right there. Sum of the first 12 terms will be 408. Anybody get those?
I did.
All right. Okay, that's classwork number 1. All right, now what are we doing with this? Let's see. I think we're doing the same thing, aren't we? 9 through 24, so we're doing the same thing here. All right, for this problem here, there's number 21. There's the answers to number 9. All right, number 21, I want you to add this to classwork 1. We're going to redo this over again, but we're going to use this sequence here. I want you to find, hold on, what do they want us to find here? All right, they want us to find the first 5 terms of this arithmetic sequence. Basically, you're staring at them. That question's answered. They want you to find the common difference. They want you to find the, well, what else they want you to find here? The 12th term, and then the sum of the first 12 terms. So hold on a second. Let me do my snipping tool here. Okay, let's go down to this problem here. So we're going to do 21 here. And I want you to answer those questions for number 21. Find all 5 of the 4 of those things, okay? For number 21, that's part of classwork number 1. Okay, the first 5 terms of the arithmetic sequence are listed. That was a given problem, a given answer, no work necessary. Common difference can be found by taking any term and subtracting off the previous term. I took 19/24, subtracted off 1/8. Common denominator is 24, multiplied 1/8 by 3/3 to build it up to an equivalent fraction of 3/24. 19/24 subtract 3/24, so 16/24 reduces down by 8 down to 2/3. Your common difference is 2/3. To find the 12th term, I use my nth term rule. First term plus 12 minus 1 times the common difference. First term is 1/8 plus 12 minus 1 is 11 times the common difference of 2/3 is 1/8 plus 2/3 times 11 is 22/3. Common denominator of 3 and 8 is 24. Multiplying 22/3 by 8/8 and multiplying 1/8 by 3/3 builds the fractions up into equivalent fractions with the common denominator 24. Adding them together, you get 179/24. That would be your 12th term of this arithmetic sequence. To find the sum of the first 12 terms, we use our formula where n is 12. We need to know our first term and our 12th term. First term is 1/8. The 12th term we found in the previous problem is 179/24. 1/8 plus 179/24 forces me to get a common denominator of 24, multiplying 1/8 by 3/3 to build it up to 3/24. 3/24 plus 179/24 is 182/24 times 12. I reduce the 12 over the 2. 2 divides itself once, divides into 12 6 times. Get it down to this. Then I cross cancel. 6 divides into itself once, divides into 24 4 times. 182/4 reduces down to 91/2. That's the sum of the first 12 terms of that nasty, messy arithmetic sequence. Anybody get those answers? Anybody get them? Are we getting this, ladies and
Um,
I got A, B, and C, but not D.
all right, D is a little bit nasty because you're working with a lot of fractions. So, but there's the breakdown there. I'll let you get that down, or this is being recorded anyway, so it's up to you however you want to get that. But yeah, you got to get a common denominator, equivalent fractions, and then you got to go from there.
yeah, the fractions threw me off.
Fractions always bog just about everybody down that I've ever met. All right, but that's how you would wade through all the fractions. Common denominator 24, equivalent fraction of 1/8 would be 3/24. Then you can add the numerators. I reduced the 12 with the 2 down to 6. And then I cross reduced the 6 and the 24. 1 and 4. Then I reduced by 2 down to 91/2. Okay. All right. So working with these formulas with arithmetic sequences. All right. Okay. Sometimes you have messy arithmetic or geometric sequences. You may not always have nice integers. Sometimes you can have decimals or fractions for the terms. Okay. All right, classwork number 2, do number 25, answering questions A through D. They give you the first term of a geometric sequence and the common ratio is 2. They want you to find the first 5 terms and write those down. What's the common ratio? Find the 12th term and find the sum of the first 12 terms of this geometric sequence. We'll call this classwork number 2, okay? Number 25, A through D. Go ahead and do that. All right, ladies and gentlemen, the first 5 terms of this geometric sequence are gonna be 12. 12 times 2 is this, 24 times this is this, 48 times 2 is this, 96 times 2 is this. These are the first 5 terms. The common ratio is 2. 12th term is gonna be the first term times the common ratio raised to the 12 minus 1 power. That's to say 12 times 2 to the 11th power, which is 24,576. You're gonna need a calculator to help you out here. Sum of the first 12 terms using our formula. This is the first term, 12 times 1 minus the common ratio to the 12th power divided by 1 minus the common ratio of 2. When you work this out on your calculator, you'll get 49,140. Anybody get those answers? Well, that's working with the geometric sequence a little bit there. Real good. Anybody get those answers at all, or
No, I didn't get that.
all right? Well, you're seeing how they're done. At least you can go from there. And you'll have to look these formulas over and just kind of put them into the memory banks. It takes a little bit of time, but the formulas we went through, the nth term rules, and also the sum formulas.
Okay.
And of course, when you do Alex, you have that wonderful button that you can click on that says show me an example, and it walks you through a complete example step by step. And that's invaluable to helping you to understand how the problems are done. It's always wise to also look at the examples that are laid out in the section of your textbook for all the sections that I cover. By looking through the examples, that also helps you to give you more looks, okay, more problems, and it shows you how the problems are worked out. And that also gives you a better understanding as to what's going on. So when you go to do Alex, you'll be more successful. Okay. So I would recommend you always look through the examples in the textbook. You're welcome to do odd problems in the textbook, and the answers should be in the back of your textbook for odd problems in your book. Although they're not going to be assigned, formally, they're there for your practice if you want them. All right, so we'll call that class. What was that? Yeah,
I have a question on D. What did that turn into? Did that turn into a 5 or is that an S?
No, this is S. This is the sum of the first 12 terms.
Okay.
Okay. Yep. Sum of the first 12 terms. And we're using our formula that we derived, okay, to crank that out. So the sum of the first n terms of a geometric sequence is always computed by using this formula, okay? Yeah, that's the formula we use. All right, that's classwork number 2. Okay. Let's see what else we got here. All right, problem number 44. Is this an arithmetic or geometric sequence? Number 44. Problem 44. Is that arithmetic or geometric?
Geometric.
It's a what?
Geometric. I might be wrong.
Okay, you're saying geometric. Okay, what do you think the common ratio is if it's geometric? You are well, let's see, is there a common ratio? If I take 4 and divide it by 2, what ratio do I get? 2?
2.
Is that equal to 12 divided by 4?
No.
And is that equal to 48 divided by 12? It has to be if there's a common ratio. Is that true?
Oh yeah.
This isn't true at all, is it? 4 halves is 2, 12 fourths is 3, 48 twelfths is 4. This is not geometric, or it's what? Not arithmetic. It's neither. You see that there? Doesn't have a common difference or a common ratio. Doesn't have a common ratio difference either. 4 minus 2 is not equal to 12 minus 4, which is not equal to 48 minus 12, and certainly is not equal to 240 minus 48. That's neither geometric or arithmetic. How about number 45? Arithmetic, geometric, or neither?
Is it
What's that?
arithmetic?
Arithmetic? Okay, you're saying arithmetic? Okay, if it is arithmetic, it should have a common difference. What do you think it is?
-4.
Yeah, if you take any term, like 2, and subtract off the previous term, like 6, that should be equal to, if I take -2 and subtract off the previous term of 2. And that better be equal to, as if I take -6 and subtract off the previous term of -2. Certainly, it does look like in each case, we're getting a common difference of what? -4? You are correct. That's arithmetic with a common difference of -4. Let's check our answer here. Yep, it's arithmetic. Okay. All right, a little more difficult one, ladies and gentlemen. And use your calculator to help you out a little bit here. Number 46. Do you think 46 is arithmetic or geometric? Now, to determine if it has a common difference, you can do it one of two ways. You can either ask yourself, what would I have to add to 1/10 to give me 3/40th? Or you can take 3/40 and subtract off 1/10. Those are basically the same, asking the same question. What would be the common difference? So does it have a common difference? Well, if it does, then 3/40 minus 1/10 has got to be equal to any other term minus its previous term. Is that the case, to say that this would be equal to 9/160 minus 3/40? True or false? And is that to say that that would be equal to 27/640? Minus 9/160. Okay, does it have a common difference?
No.
Oh, you can use your calculator to help do the crunching of the numbers. You know, you take 3/40 minus 1/10. Another name for 1/10 is to say 4/40. So if you take 3/40 and subtract off 4/40, you're going to get what? You're going to get -1/40, correct? Is -1/40 9/160 minus 3/40? In other words, is 9/160 minus what's an equivalent fraction of 3/40 with a denominator of 160? You'd have to multiply 40 by what? By 4. So you're going to multiply the numerator by 4. So 4/4 times 3/40 is 12/160. Now, what's 9 minus 12? That gives you -3/160. Does -3/160 reduce down to -1/4? Are these equal?
No.
They have to.
No.
They have to be if this is an arithmetic sequence. It has to have a common difference. I don't know about that. That don't look like they're equal. No, it doesn't look like they're equal at all. That's enough to shoot this out of the water. So, ladies and gentlemen, this is not arithmetic. Is it geometric by chance? Well, let's see. What would you multiply 1/10 by to give you 3/40? It's not arithmetic. What would you multiply 1/10 by to give you 3/40? Well, you could multiply it by what? 3/4? That gives you 3/40. Well, okay, if you're calling 3/4 your common ratio, then you had better be able to multiply 3/40 by 3/4 to build it up to 9/160. Is that true? If I take 3/40 and multiply it by 3/4, do I get 9/160? Oh, wait a minute, it's looking pretty good, isn't it?
Oh, yeah.
Now, if I take 9/160 and multiply it by 3/4, do I get 27/640? If I multiply this by 3/4, do I get 27 over 640. It's looking pretty darn good. Do you agree?
Yeah,
Yeah, this is geometric, ladies and gentlemen. Common ratio turns out to be 3/4. So it's geometric with a common ratio of 3/4. There you go. All right, for classwork 3, I want you to do number 47. Is this an arithmetic sequence, a geometric sequence? And if it is, what would be the common difference or the common ratio? Or maybe it's neither. Okay, we'll do this for classwork 3. Go ahead. Number 47. All right, I tried to see if this was an arithmetic sequence first by taking a term and subtracting off the previous term for several adjacent terms, and in each case, I was getting the same difference of -1/2. So it does look like this is an arithmetic sequence. And since I did find a common difference, you do not have to waste your time to try to find a common ratio. It's not going to have one. And so it's definitely arithmetic. Did anybody else concur with this result?
Yes.
Alrighty. Well, ladies and gentlemen, that's it for today. We covered arithmetic and geometric sequences. We also developed some formulas that will enable us to crank out any nth term of such a sequence, and also to determine the sum of the first n terms of these sequences. I would have these formulas handy when you go to sit down by Alex and do some problems, either that or have them memorized. And make sure you have a scientific calculator handy too. Okay. All right. So I will be opening up the problems out of this, updating Alex with the homework, bringing it up to section 5.7. All right. Well, have a good weekend. And if you have any questions or concerns, I'll be on the line for a couple minutes. All righty. So take care.